Hi everyone. In this video, we'll look at some convergence tests for series that have both positive and negative terms. In particular, we're going to develop specific convergence tests that work when our series have both positive and negative terms. We'll determine when series with these positive and negative terms are convergent or divergent. And we'll also understand absolute versus conditional convergence and the implications of those properties. So to begin with, let's first talk about something called the absolute value test. So the absolute value test says that if the sum of the absolute values of the terms of a series converges, then the sum of the terms of those series also converges. Okay. So to see why this is true, it's actually just an application of the comparison test. But we're actually going to start by looking at the sum an plus absolute value of an. If we look at this series, one of the things we know about an is that an is always between its absolute value and negative its absolute value. This is just a property of the absolute values of real numbers. And essentially, it's always equal to one of these, right? So if an is 4, then it's equal to positive its absolute value. If an is -4, it's equal to negative the absolute value of -4. But because of this, if I add absolute value of an in each term, I get this. And if I assume that this series converges, that would mean that the sum to absolute value of an converges. And therefore, by the comparison test, that tells me that the sum an plus absolute value of an converges. Okay. But then I can write the sum of the an's as sum of an plus absolute value of an minus the sum of the absolute value of an's. But now this converges by hypothesis, right? I'm assuming here that the sum of the an's converges. I've proven that if that sum converges, then this converges. And so now this is a difference of two convergent sequences, so it also converges. So this is a nice little test that sort of quickly falls out of our comparison test. It's not important that you necessarily remember the proof. I just want you to sort of see where this comes from. But let's see in practice how this can be used to help us when our terms involve both positive and negative terms. So let's start with this series. So to begin with, just a bit of terminology. This is a type of series, a special type of series called an alternating series. Okay. So this test, the absolute value test, works for any series that involves both positive and negative terms. This is a special kind of series called an alternating series because the signs flip-flop back and forth as you go through the term. So when n is equal to 1, this is negative. When n is equal to 2, it's positive. When n is equal to 3, it's negative, positive, negative, positive, negative, positive, negative, positive. So this is a special type of series involving both positive and negative terms called an alternating series. Okay, but nevertheless, let's see, what does the alternating series test tell me? It says, well, if this series converges, then that series must converge. I need to determine if this converges. Well, what is this series? Well, I've got the absolute value of this fraction. I can rewrite that as the absolute value of the top over the absolute value of the bottom. Now, keep in mind our n values, right? These are positive integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, so on and so on. So those positive numbers cubed are already positive numbers. I can drop the absolute values there, right? The absolute value, because these are already positive, the absolute value of n cubed is just going to be equal to n cubed. Okay. Now, in the numerator, what do I have? I have these things, they flip-flop back and forth, -1 + 1, -1 + 1, -1 + 1, so on and so on. But when I take the absolute value, well, if it's +1, I just get 1 back. If it's -1, I just get 1 back. So the absolute value of -1 to the n is just 1, right? Whether this is positive or negative 1, its absolute value will be 1. But now this series, I know that this converges, right? Why? Well, it's a p-series. So by the p-test, I've got a p of 3, which is greater than 1, so this converges. And so I now know that this series converges by the absolute value test since this series converges, right? And this series, right, is the absolute value of the terms of this series, right? So again, sometimes this is a really easy test, right, to apply. This just, I hit all the terms with absolute values. That gives me back a p-series. That's great. Now let's look at another example here. I have the sum of cosine of n pi over n. Okay. Now again, in this case, if I want to try and apply the absolute value test, I would look at this and I would say, okay, if I hit each of these terms with absolute value, I get that. Now in the denominator, that n, those are just 1, 2, 3, 4, 5, 6, so on and so on. Those are already positive, so I can drop the absolute values. I need to think a little more carefully about this term up here. So when n is equal to 1, that's cosine of pi. Cosine of pi is -1. When n is equal to 2, cosine of 2 pi is 1, and I get 1. And what you actually will quickly start to realize is that cosine of n pi, that's actually just a sneaky way to write -1 to the n, right? If you think about the unit circle, right? So you have 1 here and -1 here. So when you're at pi, you're over here. You get -1 when n is 1, then 1, then -1, then 1, -1, 1, -1, 1. So you actually get -1 to the n. So again, its absolute value is just going to be 1. But now the problem you have is that this doesn't converge anymore. This series diverges. Now the absolute value test says if the series of absolute values converges, then the series converges. It does not tell you anything about what happens when the series of absolute values diverges. So in fact, here, the absolute value test is inconclusive. We can't conclude anything in this case. So absolute value test is great as long as that series of absolute values converges. If it doesn't converge, or if it's just something we can't really figure out whether it converges or diverges, then the absolute value test isn't of much use. Let's look at one more example here. Again, if I wanted to apply the absolute value test here, I would say, okay, I want to look at the series of absolute values. So again, I'm taking the absolute value of the whole thing, but that's the same as the absolute value of the top over the absolute value of the bottom. Now, this is essentially like minus 1 to the n. It alternates back and forth between minus 1 and 1. The difference is it starts when n is equal to 1, you get negative 1 to the 1 plus 1, or negative 1 squared. So this starts at 1, whereas minus 1 to the n started at negative 1. But still, it just alternates back and forth between 1 and negative 1. So its absolute value is 1. This bottom term here, always positive. Right? Anything squared plus 1 is certainly always positive. And so I get this series. Now, this is not one that I can immediately look at and say, oh, I know that this converges or I know that this diverges. But I probably have a guess. I think that this should behave like 1 over n squared, which I know converges. Okay, so right now I have a question, essentially, does this series converge or diverge? Okay. Well, in order to determine that, so let me sort of pose that as a separate question. Well, to determine that, if I think this behaves like 1 over n squared, I might try either comparison or limit comparison. Okay. Let's say I wanted to do, let's do comparison. So I have 1 over n squared plus 1. If I make the denominator smaller, that'll make the whole thing bigger. Okay. So since that's true, and I know that this converges. Why do I know this converges? It's a p-series. Okay. Now I've got that the bigger of the two series converges. So the sum 1 over n squared plus 1 converges by comparison. All right. So now what have I done? I've used the comparison test. So I know that 1 over n squared converges. I've used a comparison test and that fact to determine that the sum 1 over n squared plus 1 converges. And now since this series converges, this must also converge by the absolute value test. So what I really want you to see in this example is once you take the absolute value, now you need to determine whether or not this series converges. But to determine whether or not this series converges, you may need to apply some previous tests. Now, the nice thing here, all of our previous tests were based on the assumption that the terms of your series were positive. Well, guess what? When you do the absolute value test and take the absolute value, you're going to end up with a series whose terms are always positive. So this is really nice because I'm guaranteed to have something that at least meets one of the criteria to apply my previous test. Now, if you want to get in a little extra practice, you could go back. You could also prove that this converges by limit comparison. Or actually by the integral test. So if you want a little extra practice, go back and see if you can prove that this integral converges by the limit comparison test and the integral test, but it also works obviously by the comparison test. Doesn't matter how we get there. The important part is once we know this converges, then by the absolute value test, this must also converge. So a couple of remarks about the absolute value test. The only possible conclusion of the absolute value test is that a series converges, right? The absolute value test says if the series of absolute values converges, then the series converges. So you'll never write a sentence that says this diverges by the absolute value test, because that's not a valid conclusion from the absolute value test. So when that series of absolute values diverges, we can't actually conclude anything, right? If the series of absolute values diverges, then the original series could still converge or it could diverge. We just don't know. So let's give you a chance to practice this on your own with a quick knowledge check. What does the absolute value test tell you about the series below? So this is the sum sine of n over n. So take a moment, try to apply the absolute value test and see if you can learn anything about this series. Okay, this is maybe so far one of the trickiest knowledge checks I've given you, because there's a couple of places where you could sort of go wrong here. So if I think about applying the absolute value test, and take the absolute value of the terms. Now, you might be tempted to go, oh, earlier we had cosine of n pi and absolute values, and we just replaced that with 1. We can't actually do that here, right? Because I don't have a pi here. So these values actually, if you think about it, for small values of n, it'll start off positive, then it'll switch, it might be positive for a couple terms and then negative. Like, you don't actually know that this is alternating, and it's certainly not alternating like just between plus and minus 1. Now, in the bottom, you can drop the absolute values. Okay, you get this. And now you want to try and determine whether this series converges or diverges. And it actually turns out that none of our tests are really going to help us out here. If you think back through our other tests, so just sort of starting from the beginning, this limit will go to 0. Okay, so that's not going to help. So the test for divergence doesn't tell us anything. We could then try the integral test, but I need to be able to integrate this, and I'm not really going to be able to integrate that very easily. I could try, it's not a geometric series or a p-series. Then I could try comparison. So that might be where you think, okay, I could try comparison because maybe I know that, right, I know this is true. This is not always equal to 1, but it's certainly always less than or equal to 1. And oh, I know that this series diverges, but that's the bigger series diverging, which doesn't tell me anything about the smaller series. So that doesn't help either. You could try, maybe you think, oh, but maybe it does behave like 1 over n. If you try that and try to do limit comparison, you'll actually get a limit that doesn't exist. This is a really sort of nasty series to have to deal with, okay? So in fact, the absolute value test, based on what we know so far, doesn't really tell us anything about this. It actually turns out that, well, we'll actually come back to this series a little bit later to talk about it, but none of our tests really help deal with this series. So all the absolute value tests can tell us is if this converges, then that converges, but we can't really learn anything here. So the absolute value test, based on what we know right now, is really inconclusive for this series. Now, we saw a couple of examples of what we called alternating series, and it turns out there's actually a special test for alternating series. So an alternating series is just any series of the form minus 1 to the n times an, or minus 1 to the n plus 1 times an. Essentially, they need to alternate signs between positive and negative, but it doesn't matter whether it starts positive or starts negative. So that's really the only difference between these two, is that one starts negative and one starts positive. So the alternating series test says an alternating series converges if This first condition, what is it saying? It's saying that the n plus first term is always less than or equal to the nth term. This is saying that the sequence of terms is non-increasing. So often we see examples they're decreasing. They don't have to go down, but they can't go up. So that's the first condition. The second condition is that the limit of the terms should be 0. So if the limit of the terms is 0, and if the terms are decreasing, or at least non-increasing, then the alternating series will converge. Now, to sort of roughly understand why that's true, we can think about sort of a plot of the terms. So sort of imagine, lower this a bit. So on this axis, I'm plotting the ANs and the Ns. So they're alternating. So let's assume we're in the case where the first one is positive. If the first one's negative, the argument essentially is the same. So if the first one is positive, then it's going to be up here somewhere. Okay. Now the second term, right, is decreasing, right? But the second term is going to be negative. But you know it's not going to be as far down as the first term was up, right? So it's going to be maybe here and then maybe here. So each time they've got to be getting closer to the axis here, but they're alternating or flip-flopping sort of what side of the axis they're on. Now, let's think about the effect that must have on the partial sums. So if you think about the partial sum, well, the first partial sum, right, is always just the first value, right? So that's going to be actually exactly at the same height as this. So the first partial sum is sitting here. Now the second partial sum, I'm going to add these two values. Well, this one's positive and this one's negative. But what I know is that this one is sort of said this is not mathematically precise, but this is more positive than this is negative. That's because of this condition here, that the sort of the absolute value of the terms is decreasing. So what's going to happen here is that this is definitely going to go down. Okay, but it's not going to drop to be negative. Now, I'm then going to add back in a little bit. Okay, well, let's see. What's going to happen when I do that? I'm going to add back in a little bit. Okay, but I know that the sum of these two together has to be negative because this is more negative than this is positive. So what that tells me is I'm going to go back up a little bit, but I'm not going to go all the way back up to here because the net effect of these two is still going to be negative. Okay. And so I can sort of keep going in this way. And what I actually see is that my my partial sums are actually bounded between the first and second partial sum. And what I can essentially show, if you want to rigorously prove this, which is a little outside the scope of this class, but I want you to get the sense, you can essentially show that what happens long term is that you get some sequence that's bounded, and you can show that sort of odd terms are decreasing and even terms are increasing. They're bounded and they have to converge to the same thing, essentially. So it's a little, there's a little bit of technical precision required. In a course in real analysis, you might prove this result. But I want you to get a sense for why this works here. Now, again, these two conditions only work if your series is alternating. If your series is not alternating, these two conditions don't tell you anything. Okay? But if your series is alternating, then this will tell you that your series has to converge. So let's see in practice what applying the alternating series test looks like. All right, so the first question we have to ask ourselves if we're going to apply the alternating series test is this an alternating series? Well, this is minus 1 to the n over n cubed And certainly if we want to sort of write it in that form, maybe we're a little more used to seeing alternating series in. Right, I could write it like this, and now this is like what we're calling our AN. This is the alternating part here. Okay, so you really first split your sequence in or your series into the alternating piece, and then this is sort of the rest of it. Okay. So now we'll take a look at this series, at these terms, the non-alternating part, and see what we can say. Okay, so if I want to apply the alternating series test, the first thing I want to ask is this decreasing? Okay, so I really want to know, how does a sub n plus 1 compare to a sub n? Well, let's see, a sub n is 1 over n cubed. A sub n plus 1 would be what? We'll replace the n with n plus 1, so it'd be 1 over n plus 1 cubed. Well, if I look at these two, the numerators are the same. This has a bigger denominator. If this has a bigger denominator, right, that one certainly has to be the smaller one. Okay, so we get our first condition is met, right, which is that the sequence is decreasing, and certainly all of these are always positive, right? So our first condition is met. Now we just need to look at the limit as n goes to infinity of an. So that's going to be the limit as n goes to infinity of 1 over n cubed. And certainly that is 0. Okay. And so that's the second condition of our alternating series test. And so this series converges by the alternating series test. So really nice test, right? You essentially just check these two conditions. You know, this first one, depending on the series, can be harder or easier, right? In this case, it wasn't very difficult to establish this inequality, but for other series, it could be a little more difficult. And then you take a limit, you check this limit condition, but if you get sort of checks for both of those, then the alternating series test tells you that your original series had to converge, okay? Now, I do want to point out, this does not necessarily tell you anything about this series. Okay. Now, in this case, it does turn out that this series also converges. But in general, you don't know anything about the series that's not alternating based on the fact that the alternating series converges. So just be careful. There's sort of a limitation there in what it tells you. Let's look at another example. What about the alternating series minus 1 to the n over n? Now, you may be sort of thinking, well, if I split this up, I sort of think about minus 1 to the n times 1 over n. And you might be thinking, oh, no, I know that this diverges. Okay, so for example, if you were to try and apply the absolute value test to this, if you took the absolute value of the terms of the series, you'd get this. This diverges. But remember, the absolute value test, when the series of absolute values diverges, it doesn't tell you anything. So we still don't know whether this series converges or diverges just because we know that this series diverges. Since this is an alternating series, let's try the alternating series test. So again, there are the two conditions we need to check. So the first thing I'm going to do is I'm going to write down an plus 1 and an. Always easier to write an first, right? That's just going to be the 1 over n piece here. Then an plus 1 will be 1 over n plus 1. Well, pretty easy to see. This one has the larger denominator, so it'll be smaller. And of course, these are both greater than or equal to 0. Okay, and so this first condition is met. My sequence of terms is non-increasing. Now, the second thing I need to check is that limit condition. So I need to check the limit as n goes to infinity of an. That's just the limit as n goes to infinity of 1 over n, and certainly that limit is 0. So that second condition is met since my limit of the terms is 0. So this series then converges by the alternating series test. So again, this alternating series converged even though the series of absolute values diverged. Okay? So again, there's no relationship between whether or not the alternating series converges and whether the sort of absolute value, the series of absolute values converges. You may remember that this series here was called the harmonic series, and the harmonic series diverges. This series here is often called the alternating harmonic series. Oh, it is an alternating series, but this is the alternating harmonic series. Okay. So the alternating harmonic series converges while the harmonic series diverges. So a couple of notes about the alternating series test. The first is that this test is great, but it only works when I have an alternating series. So if I think back to that example we were looking at in the last knowledge check, I can't apply the alternating series test here because I don't know that this is alternating, right? So let's see, sine of, if n is in radians, then sine of 1 will be positive, sine of 2 will be positive, sine of 3 will be positive, sine of 4 will be negative, sine of 5 will be negative, sine of 6 will be negative. So it's not alternating, but it does include both positive and negative terms. So since it includes both positive and negative terms, I can't use things like comparison or limit comparison or integral test. Because it's not alternating, I can't use the alternating series test. So far, the only test we could even think about using would be the absolute value test, but we saw that that wasn't very helpful either. So the alternating series test is great, but you have to be working with the alternating series, that signs are alternating between positive, negative, positive, negative, positive, negative, okay? The good news is, often though, when you have an alternating series, this is the best series to use. Or sorry, this is the best test to use. Okay. Now, we've sort of started to see a difference here, and we're going to actually define something called absolute convergence and conditional convergence. So when we have series which contain both positive and negative terms, we can actually differentiate between two different types of convergence. So the first is if we have a series that converges and its series of absolute values converges, then we say that that series converges absolutely. Okay. So for example, minus 1 to the series minus 1 to the n over n squared, you can show this converges. Oops, a little hard to see. Minus 1 to the n over n squared, this converges. You could show that by the alternating series test. The absolute value of these terms is 1 over n squared. This series also converges. So we would say that the sum minus 1 to the n over n squared converges absolutely. So if the series and its absolute series of absolute values both converge, then we say that that original series converges absolutely. Okay. Now, this is different if the series of absolute values does not converge. Okay. So if we have a series that converges, but when you take its series of absolute values, it does not converge or it diverges, then we say that that series converges conditionally. So let's go back then to the alternating harmonic series, which converges. But the harmonic series, which is the series of absolute values of these terms, it diverges. And therefore, we would say that this series converges conditionally. Now, you might wonder, why make this distinction? There's sort of two reasons, one sort of theoretical, but one very practical. The first sort of reason is that, well, one is just sort of stating that something's converging a little bit stronger. So absolute convergence is stronger than conditional convergence. Absolute convergence means not only do I converge as a series, but my series of absolute values also converges it. So I sort of have this stronger condition that I satisfy. Whereas conditional convergence is a little bit weaker. Yeah, I converge, but my series of absolute values doesn't converge. But there's another practical reason for this, and that is that series who converge absolutely, you can rearrange the terms in the series and it'll still converge to the same value. Whereas with conditional convergence, you don't necessarily get that. Okay. So let's pause for a moment. Let's have a quick knowledge check. I want you to take a look at the series below, and I want you to determine whether or not it converges. And if so, I want you to try and determine whether it converges absolutely or conditionally. So take a moment and see if you can determine whether this series converges or diverges. I will note here that you can choose either test, the alternating series test or the absolute value convergence test to try and determine whether this converges. Okay, great. First, let's talk a bit of strategy. Anytime you're asked whether a series converges absolutely or conditionally, it's almost always a good idea to start with the absolute value test. Why? Because if the absolute value test works, then you're done and you know your series converges and converges absolutely. If the absolute value test fails or is inconclusive, then you move on to the alternating series test. Okay, so let's start this by looking at the absolute value test. So if I were to take the absolute values here, so I'm going to take absolute value. Okay. Now, this is positive. A little hard to maybe see here, but this is always positive. Okay. And so the only thing that's changing here is this. So in the absolute value, I'm just going to get n squared plus 1 over n to the fourth plus n minus 1. Okay. Now the question becomes, does this series converge or diverge? Well, if I look at this, I sort of probably think, if I look at highest powers, this should behave like 1 over n squared, which I know converges. Okay, so now I'm going to do limit comparison of this to this, right? But this is actually exactly a type of problem we've done before. So you can check here, right, that this converges. And so by limit comparison test, this also converges. And now since this converges, you now know that this series converges absolutely by the absolute value test. So the absolute value test is really nice because if the absolute value test works, then you not only know that it converges, you know it converges absolutely. Okay. And so I almost always, if I'm asked whether it converges absolutely or conditionally, I'm going to start with the absolute value test. If the absolute value test had failed here, then I would go back and try the alternating series test. If the alternating series test then worked, I would know that it converges conditionally, but not absolutely. But since the absolute value test works here, I actually know it converges absolutely. Now, lastly, I just want to mention, again, I sort of started mentioning this earlier. If you have a series which converges absolutely, then you can take the terms in the series, rearrange them, and the series will still converge, and it'll still converge to the same value it converged to before. Now, you might feel like, well, of course, that's always true. That's always true for finite sums, right? 2 plus 3 is 3 plus 2, right? Addition is commutative. But when we're talking about infinite sums, an infinite number of terms, that's actually not always true. And so it turns out that if your series converges absolutely, then yes, you can rearrange the terms and your series will still converge to the same value. However, if your series converges conditionally, then something really, really interesting happens, which is actually that you can take any real number you want, and there's a way to rearrange your series so that that series will converge to that real number. So if you take the alternating harmonic series, you can take and rearrange the terms so that it converges to pi. But you could also take and rearrange the terms so it converges to 73. And you could take and rearrange the terms so it converges to negative e to the fifth. Um, so when things converge conditionally, there are strange things can happen, right? I can rearrange terms and get different sums for my series. But that's also a really powerful tool sometimes that we can take advantage of in math. So I hope this has helped answer a lot of questions you may have had sort of as we've been working through and developing all these tests that only deal with series that have positive terms. Now we know how to handle series that have both positive and negative terms. As always, you'll have a chance to practice this in the homework and the quiz. And please reach out if you're having any difficulty with this material, if you didn't understand anything we covered in this video, or if you need any assistance with the homework.